So just one administrative thing. You guys hopefully have all seen that the project phase 1 was posted late yesterday in the afternoon. And pretty much by the end of lecture today, you should at least have a rough idea as to kind of what the important things to think about in the project there are. So definitely go ahead and get started on that. That'll be due next Friday, so a little bit more than a week from today. And just to kind of keep you on your toes, there'll be yet another phase of the project due about a week after that. So make sure you definitely get going because things will start coming at a fairly rapid pace. As I said, the first 2 phases of the project will be a little bit more, let's say, homework-like, and that there won't be as much sort of complete freedom to do whatever you want. But by the time it hits phase 3, it'll really be completely open. You'll have a lot more sort of complexity to actually be dealing with. So again, very good idea to get started on this stuff ahead of time rather than late. Yes? Yeah, so I may shift the second phase by like a couple days, depending upon when we post it and and things like that. But basically, it's indeed to leave as much time as possible for the third phase, because that's where you really have to sort of do a lot more exploration and thinking about how to balance out different pieces of the whole system. Other questions on logistics or material or anything like that?
Yeah, you mentioned the part you mentioned something about comparator offsets.
I'll talk more about it today. Yes. So the question was about, the project comparator offset. Don't worry, I'll talk more about it today. By the end of today, what exactly, you need to be doing in the project should be much more clear. All right, great. So with that, let's go ahead and sort of dive back into the material. Oh, yes.
Are you supposed to build the whole schematic that's shown or just the amplifier?
No. So the question was, for the project phase 1, are you building, everything that's shown there? You're only building that front-end amplifier for this phase. Don't worry, by phase 3, you'll be doing everything that's there and more. But for this phase, you're just doing the amplifier. OK, great. So let's go ahead and dive back into the material. So last time we were talking about biasing and references. And we basically, I believe, finished up at sort of the constant VGS reference, which was, we have sort of first introduced the, let's say, funky way of getting things to actually self-bias themselves, where we basically had, we basically said, well, we needed a bias current somewhere, and if we had a voltage across a resistor, that would create a current. We basically just mirrored it back around to use that for the bias current we needed in the first place. So what I'm going to do is walk through a couple more examples similar to that one, mostly just to sort of give you an idea of how you can get different types of either references or biases that are either constant in different ways or are proportional to things that you might be interested in having them be proportional to. So as an example, one very sort of, let's say, classic reference is a so-called proportional to absolute temperature reference, or the PTAT reference. Okay? And as you'll see in 1 second, it's very common for all of those sort of temperature-dependent kind of things to rely on some sort of diode or bipolar junction transistor somewhere. So let me draw sort of a typical implementation of this particular reference, and then we'll sort of walk through how it actually works. Okay? So we'll start everything out with just a couple of BJTs. But as we'll see in 1 second, we're actually going to sort of play a little bit of a game to get an interesting result out of them. So we've got these 2 BJTs here that are sort of connected in something that looks like a current mirror configuration. There's, of course, going to be a resistance right here. And then as we had done before, we're actually going to use the current we're generating in the first place to sort of self-bias the whole structure. Okay? All right, so now you might be wondering, well, how in the world does something like this tell me anything about temperature, or how does it give me a current that's somehow related to temperature? Well, to do that, we have to sort of remind ourselves what actually sets the current inside of, in general, a bipolar junction transistor, but even actually it turns out with a diode. So let's just think about a bipolar junction transistor. So if I've got a BJT, then, and let's just assume that, for example, I'll call this, just in general. So let's say I have an IC. So what is the current in a bipolar, in a BJT set by? Okay, it's voltage in kT over Q, but let's be slightly more specific. What's the sort of functional form of it? Okay, that's right. So you said there's e to the VBE over kT over Q. Okay, now this is a real bipolar now, so I'm not going to put an N in that kT over Q. I'm going to assume it's really a bipolar junction transistor. Okay? Now it turns out there's also an IS, right? There's some nominal current that you're sort of relative to. But indeed, this is the sort of typical form for the current in a BJT. Okay? All right, so I'm going to rearrange this equation slightly, because as I'm going to see in 1 second, I'm actually going to be interested in both the actual base to emitter voltage and actually the difference in base to emitter voltages between those two BJTs that I've drawn there. Okay? So let's assume that the device on the left, I'm just going to call it, sort of the device number 1. So VBE1, if I just use that sort of standard equation there, it's going to be just, and by the way, I'm going to define this KT over Q as just being equal to VT, meaning the thermal voltage. Okay? So that VBE is just going to be VT times the natural log of the collector current divided by whatever that nominal IS was. Okay? I just rearranged the equation that's above there. All right? And this would be this VBE here. Okay? Now, notice with this second bipolar junction transistor, let's call that VBE2 right here. This M factor that I indicated here is like saying that I made the area of that device M times larger than the BJT on the left. Okay? So, as you can imagine, the VBE for that one is, functionally it's going to be the same thing. It's just going to be VT times natural log of whatever the collector current is divided by its nominal current. It's just to keep in mind that IS2 there for the sort of same VBE is going to be M times larger than the IS1. Okay? So now here's something that's actually quite interesting. Okay? If you kind of look at this circuit, it should hopefully be pretty clear that given that the bases of these two devices are tied together, then the voltage that shows up across this resistor here just has to be the difference in VBEs, right? It has to be delta VBE, meaning VBE1 minus VBE2. Okay? Just because, again, if the bases are tied together, the other side is the power supply, so the only thing that could show up on that resistor is delta VBE. Okay? So let's actually look at what that delta VBE actually is. Okay, so delta VBE is, of course, just going to be VT times the natural log. And by the way, I'm going to use sort of the properties of natural logs now, where subtraction is equivalent to moving it inside and flipping it over, etc. Hopefully you guys all remember this. It's just going to be equivalent to the natural log of IC1 over IC2 times IS2 over IS1. Okay? And again, I just took, I didn't write out that step explicitly, but all I did was, when you do this subtraction, you can change the natural log, instead of subtracting natural logs, you can just put them inside of the same parentheses. Okay? All right, so now hopefully it should be clear why this is actually an interesting thing to do. Because if I really have this current mirror down on the bottom over here, and I make that just a one-to-one current mirror, then the current through these two branches should be the same, right? That means that this ratio here is just 1. And if you remember, I said a second ago that because I size this device up to be M times larger, its IS2 is M times larger than IS1. That means that now what I end up with is that my delta VBE is just equal to VT times the natural log of M. Okay? So in other words, what I'm going to get now is that the voltage across this resistor is going to be linearly proportional to the thermal voltage, KT over Q, times some constant factor that's set by how I designed these two devices. Okay? Does this make sense to everybody? Or? Yes, so basically IC is just the collector current. So this is IC1, and this is IC2. Okay, and again, just because of my current mirror, or assuming my current mirrors were perfect and I really get exactly a 1-to-1 ratio there, then that ratio should indeed just be 1. Right? So in other words, this should be 1, and that's just M. Is that clear to everybody? Or? Okay, so notice, magically, by setting up these two BJTs with slightly different current densities, but looking at essentially the difference in their base emitter voltages, I can actually get out a voltage that's proportional to the temperature. Okay? And by the way, it turns out that oftentimes voltages proportional to temperature are useful for various biasing purposes, but if nothing else, sometimes you actually want to build a thermometer. Right? Sometimes you actually want to know what the temperature really is, and by the way, this is pretty much the classic way of doing it. Okay? Does this make sense to everybody? Or? By the way, how many of you guys have seen something like this before? Okay, good. All right, so maybe one sort of quick question for you guys. So this all sounds great, but do you see any practical difficulties with actually doing this in, let's say, our 90 nanometer CMOS technology? Let's see if I can get somebody not, in this first table over here. Yes.
You probably don't have bipolar.
Yeah, okay, so I probably don't have bipolars, at least not exactly the way that I've drawn them here. So turns out you do actually have bipolars. They're just not really usually intended to be operated as bipolars. Okay? So the way to see that is following. So remember, anytime you have, a few junctions back to back, so let's say a PNP or an NPN, it's going to be a bipolar junction transistor, right? It may be a really shitty bipolar junction transistor, but it'll be a BJT. Okay? So it turns out that in CMOS, the way we actually typically build these things is to basically use these parasitic PNP BJTs. And the specific one we typically use is we've got the sort of P substrate, right? You have an N well that you'd be using typically to form an NMOS transistor, right? And then if you put a P diffusion inside of that N well, which again is typically what you'd do to build a PMOS device, then you basically have a PNP device right there, okay? The only, let's say, or one of the only practical annoyances, again, other than just that this is not really intended to be used this way, right? This is not what the process guy is really optimized for, but nonetheless, it is a BJT. Oops, let's get that to a more reasonable color, okay? The only practical annoyance is, of course, that you have to tie the substrate to ground, right? Because remember, we don't want to be forward biasing the whole rest of our sort of circuits in our chip, or rather forward biasing all the diodes in the rest of our chip, right? So that means that the collector indeed has to be typically tied to ground, all right? So because of that, the way we'll actually typically use these things is kind of in the configuration I'm showing you here on the right. So rather than sort of using those PNP devices up at the top, we actually use them, let's say, down at the bottom, where we can actually tie the collector to ground so that we can use them as we sort of have to use them in this context of the CMOS process, okay? So just like before, we're still sort of going to set up a VBE there and essentially the same VBE here. It's just that we've done it in this somewhat sort of, let's say, indirect way where we have these current mirrors sitting on top of it here, where the whole idea is that these NMOS transistors, you can kind of think of them almost like cascode devices, where if the current through here was really going to be the same as the current through there, then because their gates are tied together, that means that the two source voltages also have to be the same. Okay? So in other words, the whole purpose of that structure is really just to ensure that those source voltages are the same. Okay? Other than that, it's actually the exact same idea. Just that now, again, I'm using these sort of parasitic PNP transistors. And obviously, I've sort of set everything up to be down here at the bottom of the circuit rather than up at the top, connected to the power supply. Does this make sense to everybody? Or? Okay, so again, this is a very sort of standard type of topology. Shows up very, very often, particularly if you're trying to build like a temperature sensor or something like that. And in fact, there's another kind of voltage reference that we'll talk about in 1 second, which also very much relies on exactly this kind of approach. Okay, but we'll come back to that in 1 second. So, yes?
So how would you actually size the Q2?
Oh, you literally just make the area n times bigger. Exactly.
So is this one actually better than the previous version in terms of like power supply rejection?
So the question was, is this one any better than sort of this one? In other words, is this circuit here any better than this circuit here in terms of power supply rejection? The short answer is, well, I'll be careful. To zero order, perhaps not, in the sense of it doesn't really matter if you connected the PNP to the supply or to ground, because remember, power supply rejection is always about the difference between VDD and VSS. Having said that, this one might be a little bit better only in that I sort of have, in some senses, additional gain relative to this circuit that's trying to keep these two voltages relatively constant compared to ground. Right? So that's perhaps the only reason why it might have a little bit better power supply rejection. Is that clear? Or? Okay, great. Other questions on this? Or? All right, so now let me ask you guys a question. So is this circuit going to automatically work exactly the way I showed it to you, or is there something I probably have to add to make sure it really does work in practice? And there's one specific issue that we talked about last time that I'm getting at here. Yeah, exactly. I probably need some sort of startup, right? Because as usual, if everything starts off, meaning, for example, this is at ground and this is at VDD, so that all the transistors are basically off, it's just going to sit there, right? It's going to be stuck. Okay, so indeed, you typically need some kind of a startup circuit. Okay, so here I'm just showing you one example of a startup circuit. And the whole idea is actually pretty straightforward. Okay, so the idea is the following. It's basically saying, if I grab this voltage right here, which is kind of like mirroring the current inside of the circuit, right? If I really have no current inside of the circuit, then this transistor will also be off, which will imply that this transistor is off, which then means that this device over here will pull this node up to VDD. Okay? If that happens, that will turn on this NMOS transistor right here, which will force current to flow through that PMOS device. Right? So in other words, once there's current actually flowing through here, now there should, of course, be current flowing through here. And if you've sized things properly, of course, this NMOS device over here will pull this back down, turn off the NMOS transistor, and now you should be biased at a point that it'll actually be set by that delta VBE across the resistor in terms of the current. Does that make sense to everybody? Or? So in other words, the whole idea here is you're just going to try and detect, is there current in the circuit? And if there is not current, force some current into there, right? And once there is some current, just turn off the current that you dumped in to make sure that the thing doesn't get stuck at that parasitic point with no bias current at all. Yes, question?
Isn't it better to tie the source of M9 to ground? Because if the current source is zeroed or will still not draw any current.
Oh, okay. So you said, isn't it better to tie the source of M9 to ground? I believe you could indeed do that. Although I think the particular topology I'm showing you here is not necessarily any worse from a startup standpoint. And in fact, there's probably some advantages in that if I really tie this to ground, that's probably going to take it sort of even farther away from the real bias point it's supposed to be at, right? Because now I'm just going to be getting a bunch of current through the transistor that's not necessarily going to be flowing through the BJT, right? And so once I let go of this, I have to sort of rely on some dynamics of the capacitors and et cetera to make sure that I really start getting the appropriate current flowing through here. Whereas if I actually tie this as I've tied it now, whatever current flows through here, I guarantee also flows through that BJT. Right? And it's not that I won't get any current, because as soon as I have this transistor on, right, this is basically just the diode if you look at it down here. Right? So if I put enough sort of positive voltage there, I will actually indeed get current flowing through it. Is that clear? Or?
Yeah.
Isn't it once you start to start it up, it says I'm doing returning current probably at least somewhat through M9. Does that have an effect on sort of the operating point?
Okay, great question. So the question was, well, it seems like even after this thing, even after everything is started, isn't there still going to be some amount of current flowing through this M9? Right? And wouldn't that sort of mess up the operation? And the answer is indeed, any current that's flowing through that M9 indeed will sort of put things off of their nominal bias point. Turns out, though, that you can pretty easily make it so that this current is exceedingly small, especially because of the way we connected it. Because notice, if I really get this voltage here to actually go down to ground or very close to it, I can actually get even a negative VGS on this transistor here. Because if this VBE is, a couple hundred millivolts or 300, 400 millivolts above ground, I can actually really turn that device off. And so you're absolutely correct. Any current through here is kind of bad, but usually you can get sort of enough gain in this loop that it doesn't end up being a practical issue. It's a very good question. Okay, great. So that's actually all I wanted to say sort of in terms of the startup, but I want to come back to ask you guys a question we talked a little bit about last time, which is, notice there was always a very particular way that I chose which way I drew these current mirrors here. Right? In other words, I always had it so that I was mirroring the current that was essentially created in the branch with a resistor in it. Right? That was kind of the first thing that was mirrored. You could ask yourself, well, why wouldn't I actually just flip it the other way? So I'll just draw it kind of in a different color. So conceptually, what's wrong, for example, with me doing it this way instead? So I get rid of these two mirrors, and I just mirror it the other way around. What's wrong with that? Why do you think that I didn't actually do it that way? Why do I always do the mirror the way that's actually originally drawn in the slide? So by the way, I'll give you guys a little bit of a hint. So it should hopefully be pretty clear that I've got multiple feedback loops in this structure, right? Because just, the current mirrors feeding back on themselves, that's already clearly a feedback loop, right? Okay, so let's maybe walk through and see what kind of feedback we're actually getting, all right? So as an example, let's say that just from whatever reason, this node right here went up, okay? With the way I've connected the circuit, what would be the sign of the feedback coming back to it? Is it positive feedback or negative feedback? And by the way, you just have to trace the arrows through, so somebody will give me the answer, and then we'll do it. It is negative. Okay, so did you actually work it out, or you just get? Okay, great. All right. So yes, indeed, if that goes up, this will go up, right? This will go down, and so therefore you'll come back, and this will indeed be negative feedback. Okay. Now, by the way, where else do you think it might be interesting to check whether what is the sign of the feedback? What other node might we try it on? Just for the sake of the earlier question I was asking. Yeah, the other side of this sort of reference, right, or this PTAT reference. So let me do that just in blue. Okay, so let's say this side went up. What's the sign of the feedback now? Yeah, okay. So again, you could have just guessed, because it's 50-50 either way, but you could also work it out, which is that goes up, this goes up. That means that, of course, this goes down, which means that this goes up, and, of course, this goes up. All right? So notice, just like we had talked about with that calm mode feedback example, back last lecture, we've actually got both positive feedback and negative feedback. So now you guys tell me, why is it that I must have chosen things this way, given that I have both of these feedback loops happening at the same time? What's good about choosing things this way? Or what must be good about doing it this way? Exactly, right? So the whole trick here is that what I'm trying to do is I'm trying to ensure that the gain of the negative feedback loop is higher than the gain of the positive feedback loop. Okay? So in order to see exactly why that is, you have to do a little bit of a, let's say, detailed analysis here. But to zero order, the reason that happens is that if you remember with BJTs, or more generally with, let's say, with diodes, the incremental impedance is always proportional to the current flowing through them in the first place, right? Because if you just looked at, sort of our BJT equation here, you take the derivative of this with respect to VBE, and all you get is something that's proportional to the original current. Right? Okay, so given that that's the case, and given that I have the same current flowing through both of these BJTs, if I looked at the small signal resistance of each of these independently, what would be the relationship between them? So let's say if I looked at the small signal resistance of Q1 and of Q2, what would that relationship be? Say that again? Is it N? Because remember, I forced the currents to be the same. Yeah, it's the same, right? It's actually identical. Because if you think about it, as we had said several times in the past, GM, actually I won't even do proportional, it's simply equal to the bias current divided by the thermal voltage. Okay? Doesn't matter how big the device is, once you know the bias current, the GM is just bias current over the thermal voltage. Okay? So indeed, the output resistance of both Q1 and Q2 by themselves is exactly identical. All right? So that means that the only difference between this branch and this branch is that when I added the resistor in, now instead of just having the resistance of the BJT itself, I have the resistance in series with it as well. Right? And so again, you can do a little bit of a detailed analysis. It's actually not that bad. But what you'll see is that by always choosing this side as essentially being the one that you mirrored on in this configuration, you are indeed ensuring that the negative feedback gain is greater than the positive feedback gain. Okay? And by the way, just conceptually, the way I think of it is you have a higher impedance here, and so that makes the negative feedback gain larger. Okay? So again, you have to be really careful with all these references. You might think you can just draw these diode connections any which way you want. Actually not. All right? You have to be really careful to make sure that the side that you're implicitly choosing as the reference current had better be the side that guarantees you actually have larger negative feedback gain than positive feedback gain. Yes?
Or just check on the right side, when I was looking at the arrows and the feedback, is that arrow indicating the source is going up or that the gate is going up?
Oh, so this red arrow here, you mean?
Yeah.
Yeah, so what I was indicating here was that originally the source was actually going up.
Oh, okay.
Okay, so I was asking if I was to wiggle something on the source, what would happen coming back to the source due to the circuit configuration above it?
Okay. Why does sorry, on the other side, why does the other red arrow go down?
This red arrow
Is
here?
that indicating is that the gate of M1 or is that the
It's both the gate of M1 and the gate of M2.
okay, so it's not the gate of M3 though.
No, it's not the gate of M3. The gate of M3 is over here because it's the same as the gate of M4, or the drain of M4. Sure. Yes?
You also argue that M2 is sort of tied into the source to lower configuration, so when the source goes up, the gate also goes up.
Oh, so the question was, could you argue that that M2 is in a source follower configuration? It is kind of in a source follower configuration, but just to be clear, usually source follower implies that if the gate goes up, then the source goes up, and not necessarily vice versa. Right? It is true that there's capacitive coupling, but at least at DC, it's usually the gate drives the source and not the other way around. Is that clear? Or?
Yeah.
Okay. Great. So again, the whole point here is just that, and I don't want to walk through exactly the details of this particular example because it actually, there's many, many different examples you can come up with. But the whole point is the way you choose which side, how you really connect these diode connected devices. In other words, which one is the reference and which one is sort of slaved to it, is exactly set by what is actually the side with a larger negative feedback, or rather the side that guarantees you actually get negative feedback rather than positive feedback. Okay? Maybe just as a hint, or rather as let's say a side note, it turns out that very commonly it is the side where you've placed a voltage across a resistor that ends up being the quote-unquote reference. Okay? So again, whenever you sort of see these things, it's very common for the sort of the reference current to actually be set by the resistor side. Okay? All right. So just very briefly, once we have this kind of proportional to absolute temperature type of either voltage or current, because notice, by the way, you get both of them out of that previous circuit, then the other sort of thing that's very, very common, or one of the most common references that you've probably heard about many times, is the so-called band gap reference. Okay? So the idea here is very simple. It just says that if we look at not just the delta VBE, which is, if I look at a voltage versus temperature, we already said the delta VBE goes up, right? It turns out that if you looked at the VBE itself, because of the way that IS changes, it actually goes down with temperature. Okay? So the whole idea with this so-called band gap reference is basically if I take a VBE and I add it with sort of an appropriate scale factor to a delta VBE, then if I do everything just right, what I should get at the end of the day is a voltage that's constant. In other words, an independent of temperature. Okay? Now, here's where I have to remind you about, remember I said in the very beginning that if you want to get a reference, it has to be sort of related to some physical quantity that has the exact same units as the reference that you're interested in. And if you don't have the right units, you have to always sort of translate from that reference to something else. Well, here it turns out that what we're actually trying to reference ourselves against is really the band gap of silicon. Okay? So the reason that this works is because what you're basically doing is you're generating a voltage that's very close to the band gap of silicon. Okay? Or at least it's very much related or slaved to the band gap of silicon. Yes? Great. So you said, doesn't the band gap of silicon actually depend on temperature? And yes, absolutely it does. So that means that when you do this, you won't really get something that's absolutely perfectly flat. It'll actually depend on temperature, if nothing else, due to the fact that the band gap of silicon actually depends upon temperature. Okay. Now, the good news is that's a relatively small variation. So it's, you can get things that are reasonably good. And then, of course, if you know roughly how things vary, you can try and come up with basically tricks that correct for those errors. Okay? So in this particular context, there's all kinds of things called curvature correction, non-ideality correction, and etc. The bottom line is indeed, though, those are all, let's say, quote-unquote hacks or second-order effects that you're just trying to fix nonlinearities that you know about or that are coming from the original non-ideality of your reference sort of physical phenomenon, which indeed is just the band gap of silicon. So I mention this again only because this is a very, very popular circuit. This pops up all over the place. It's highly likely that at some point in your future you'll actually have to build one of these band gaps. So it's a good thing to just conceptually know about. Obviously, you don't really build it exactly the way I've drawn here, but the concept is actually very, very similar. Once you understand this, you can go and deconvolve how any particular band gap is actually being built. Okay. So the last kind of reference that I want to spend a little bit of time on is a so-called constant GM reference. Okay? So we talked a bit about this, sort of at least conceptually, back in the beginning of this particular lecture. But it turns out that constant GMs are oftentimes pretty useful in that that's one of the sort of best circuits you can use to really control the gain of one of your stages. Because if you remember back in the beginning, we said that if we could somehow make the sort of bias current related to 1 over some reference resistance somewhere, then we could set our gain by the ratio of resistors. Okay? So here's what I'm finally going to show you how you would actually do this without magically invoking that I just happen to have a V star magically available to me somewhere. Okay? So as usual, this thing is going to be sort of built up out of one of these funny-looking, self-mirrored kind of structures. So up on the top, I'm just going to have a PMOS current mirror over there. Okay. This NMOS transistor here is actually the one that's going to turn out that I'm going to be setting its GM to be constant, or at least constant relative to some resistance. And so here's the sort of rest of the circuit, and then let me explain how this thing is actually working. Okay? So let me just call this RB over here. Okay, so first of all, hopefully it should be very clear that, just sort of by definition, I've got a VGS of voltage across that transistor, across the gate to the source right there. Okay? So now, much like we had sort of done with the PTAT reference, of course I'm going to have that same VGS across here. Again, just sort of by definition, right? So what I'm going to try and do is I'm going to try and set this whole circuit up so that I'm going to get V star across that RB right there. Okay? So by the way, to the extent that, you were back in the good old days where all the transistors were long channel, what's the relationship between V star and VGS? Yeah, exactly. So back in the good old days, VGS was basically V star plus a threshold, right? Now, okay, of course, this is not really exactly true, but given that that's the case, how do you think you're going to try and size this transistor right here to try and approximate this particular relationship? In other words, what voltage do you want to be showing up from the gate to the source of that transistor in order to try and get roughly a V star across this bias resistor here? Yeah, you basically want the threshold, right? So indeed, the way this whole circuit is set up is to try and make it so that that right there is just VTH. Okay? So if you want that to happen, how do you size that transistor on the right there? How big do you make it? I don't need a number, by the way, conceptually. Yeah, you make it really, really big, right? Because what you want is for the same current as is flowing right here, you want it to have only the threshold voltage of drop across it. Okay? So in other words, when you really do this, you make this guy big. And by big, it's usually like, 1,000, 10,000 times bigger than the device on the left. Okay? Obviously, don't quote me the exact number, depends on the technology, but ballpark, that's a very typical sort of sizing. Okay? So again, the whole idea here is that by doing this, I'm going to be forcing a V star to show up across that RB. And then hopefully just to remind you guys, the reason that works very nicely is that if I said that my IB is just equal to V star over that bias resistance, and if I remind you that GM is just equal to 2 times IB over V star, if you of course just plug those two things together, it tells you that GM is equal to 2 over RB. Okay? which is again giving me exactly the behavior that I had wanted. And by the way, just to be totally clear, the way you would really use this is once you take this gate voltage, right, you can then feed it to another transistor. And indeed, as long as you match the current density of this transistor with the current density of that transistor, meaning you've sized them for the same V star, then the GM of this will be tracking with the resistance or 1 over the resistance that you used inside of this bias circuit. Does this make sense to everybody? Or? Okay. Any last questions on this before we move on? Or you guys all know how to build constant, X of everything? I can just, tell you I want a constant blah, and you'll immediately show me how to do it. Okay, great. So if there's no more questions, let's go ahead and move on to the next set of notes, which is going to be very useful for the project. So for those of you who hopefully already took a look at project phase 1, you saw that what we're going to be dealing with this semester is basically the design of a so-called high-speed link. Okay, so I'm going to talk a lot more about what a high-speed link is in one more second. But before I do that, I do want to mention a little bit about why we're going to be talking about not just, let's say, some amplifiers or some other building blocks, but actually talking about some larger system. Okay? So if you remember, I said back in the beginning of the class, and hopefully mentioned a few times since then, I want to make sure that we looked at these larger systems because it's very, very simple for you to get, let's say, lost in trying to just take one particular block and optimize it for a set of specs that somebody handed to you. Okay? Because the problem is that if you just go and you take those specs and you build them, who's to say that if you didn't look at some other piece in the system, that if you didn't tweak it ever so slightly, that you didn't end up with a globally much, much better solution. Okay? So what that means is that if we really want to get you guys to exercise that kind of thinking, we have to actually look at a project that has a reasonable number of different components in it, so you can actually start making some of those trade-offs. Okay? So the bad news is that means you have to deal with something more complicated than just an amplifier. Okay? So because of that, that's why I'm going to be telling you about this so-called high-speed link types of designs, which as you'll see have actually a lot of, let's say, intricacies involved in them. But we'll try and focus on the most sort of relevant pieces in terms of really exercising the material we've been talking about here in EE240. Okay? So before we do that too much further, let me just tell you a little bit about what I really mean when I say a high-speed link. Okay? So what I mean by a high-speed link is basically if I take two chips and put them together onto a PCB, very, very common that you need a very, very high-speed communication between the two of them. Okay? Particularly if you're talking about, some state-of-the-art processing or graphics or something like this. All right? So if you look at this PCB, you can see that there's all these like traces running back and forth between a bunch of these chips, right, all over the PCB. Each of those is typically some sort of a high-speed link. Okay? Now, maybe before I go too much further, let me just see if anybody has really sharp eyes, although unfortunately on this screen it may be hard to tell. Very close. You said it was an Xbox. It's not quite the Xbox, but it's very, very similar. It's actually the PS3. Okay, so this is indeed the PlayStation 3. So, some of you may be very familiar with this particular PCB. If you ever happen to open up that, plastic casing or whatever, this is indeed the PlayStation 3. Okay, so the point is that these high-speed connections between chips, they're really all over the place. In fact, if you open up, your phone or, any other, let's say your TiVo, whatever, anything like that, you'd see a bunch of these very, very high-speed links between things just to make sure that in this particular case, I believe this is the sort of graphics processing engine, and there's sort of the main processor right here. You have to make sure those two can talk to each other at extremely high data rates. So just to give you an idea of the numbers, just this set of wires right here supports on the order of 30 gigabytes per second of traffic. Okay? Or throughput, I should say. And by the way, I didn't get any units or anything wrong. It really is 30 gigabytes per second. And by the way, this is, PS3 is now, I don't know, 5, 6, 7 years old or so. Okay, so this is even actually kind of slow compared to what you might see in even the more modern types of systems. So very, very fast, right? Lots and lots of data you're shoving back and forth. Okay? What else is it that you might care about in this kind of context? Do I care about just sort of how fast it's going, or is there another parameter that might be important? Okay, you said errors. That's true. We'll talk some more about that. What? Okay, so I think you guys are saying something very similar. You said accuracy in the data. In other words, so fine, I sent 30 gigabytes of data in 1 second. How many of those did actually get wrong? That's certainly an important thing to think about, although usually that's kind of a constraint that you basically don't really get to play around with too much in terms of designing the link itself. Anything else you guys care about? By the way, you guys are kind of nerdy, like, you're the one, you're like thinking about the individual bits. Like, what else might somebody care about?
I was going to say how many channels you need to get that.
Okay, you said how many channels you need to get that throughput. I'll be a little bit mean. You're also a bit nerdy. What if? There we go. Right? I buy my PlayStation, I plug it into the wall. I want to know, like, how much is this going to affect my power bill? Right? So indeed, as usual, you care about not just sort of how much performance it's got, but you also care about how much power this actually takes. Okay? So turns out this particular design takes about 7 watts for that 30 gigabytes per second of throughput. Now, 7 watts is a lot, but if you actually think about it, for that kind of speed is not all that bad, right? So this really says that throughout this whole sort of design project, you're going to have to be thinking very, very carefully about not just how you get the performance you're interested in, but how you do it in the minimum amount of possible power consumption. Okay? Because it turns out that, as I said before, you fast forward a few years, and they don't just want 300 gigabytes. They want like 300 gigabytes per second. And then pretty soon they're going to want like 3 terabytes per second, and so on and so forth. And oh, by the way, they don't want to pay any more power than they did before. Okay? So again, this is really going to be sort of the key challenge in making something like this work. Now, by the way, I talked about this as if it's really just, let's say, a graphics processor versus a CPU. You can see there's actually these traces kind of all over the place. So for example, there's an Ethernet connection here. This one maybe doesn't have it, but there'd be something like, a connection between a Wi-Fi and the rest of the system. So there's these links really all over the place. Okay, so this really is a sort of important design problem because it shows up in many, many different contexts. So, having said that, it's important to think about what are sort of the most basic issues we need to worry about when we're going to go and try and build these things. And it turns out that even though these systems become pretty complicated, at the end of the day, there's really only 2 very basic issues you have to worry about. So the first is so-called signaling, which literally just means physically how do you get the information from your transmitter over to your receiver. Okay? So in this particular case, it usually just means that, we generate some voltage signal over here. It gets sent along, we usually call it a channel, but you can think of it as just a wire. I'll say some more about that in 1 second. And gets received over at the receiver. Okay? The second issue is the so-called timing. Okay, so this is a little bit more subtle. But the point here is that if you think about it, if I really just have 2 completely independent chips, then all I'm sending from here to there is essentially some analog voltage waveform, right? So when it gets over to the receiver has to decide, well, at what time am I supposed to interpret that voltage waveform as being what bit? Okay? So in particular, let me just sort of give you an example. So let's say that this receiver, it uses a clock that always samples the data at sort of these red arrows that I'm indicating here. Okay? So you can see that hopefully it should be pretty clear to the receiver that, if I sample at this time, I've got these nice clean analog voltage levels, and indeed I would get the data pattern that I've indicated inside of this little cartoon here, right? But let's say from whatever reason, things are slightly wrong. And instead of sampling where I indicated, I actually end up sampling the data at, let's say, this time right here. So now, what's bad about that? Yeah, so I'm on an edge, and so if I moved ever so slightly in one direction or the other, I'm going to get a different data bit, right? In fact, things are sometimes even worse than this, because if I really just have this one wire or one connection between them, I may not even actually know what frequency I'm supposed to sample the bits at, right? Which would mean that I actually have to figure out, well, okay, how often am I actually getting new bits into my system, okay? So for most of the rest of this class, we're really going to be focusing on the signaling piece of things. But I did want to mention the timing part, because it is actually one of the sort of other key challenges in building these kinds of links, okay? All right, so having said that, I do want to spend a little bit of time just mentioning, well, what is it really that's kind of special about these off-chip communication systems? Okay? So in particular, I want to ask the question of, well, why is it that this is so different than what you do on the chip already, right? Because, hey, even on the chip, I can take some amplifier I had, I connect it through some wire to some other amplifier, and that's also a quote-unquote communication system, right? I'm getting information from point A to point B. So why is it that doing this off the chip kind of is special, that we're going to spend all this time talking about this and working on this in the project? Okay? Well, the answer is really quite simple. If you think about what you do in this case that I've drawn up on the right over there, when you do this design, and let me just draw it because that color didn't look so great. When you do this design, right, the way you usually model that wire is you say, well, that wire typically just has some capacitance associated with it, right? Just has some parasitic cap off to other places that you're not interested in. And maybe if the wire is kind of reasonably long, you even say, well, okay, maybe it's even got some resistance associated with it, right? Well, that's relatively straightforward to kind of think about, to deal with. We know all about sort of resistors, capacitors. That's pretty easy, right? Well, turns out the only reason this model actually works is just because the dimensions of that wire are relatively small compared to the sort of wavelengths of the signals we're interested in. So as an example, if I'm going at, let's say, 5 gigabits, 10 gigabits, something like that, that's going to imply I'm interested in something like 2.5 to maybe 5 gigahertz kinds of frequencies. Those wavelengths are just very long compared to the length of the wires that I'm talking about. Whereas if I think about one of these off-chip kind of things, this whole PCB could easily be 8, 10, 12 inches on a side, right? So each of these wires could easily be several inches long. Now, actually, they're very comparable to the wavelengths you're interested in, okay? So because of that, we can't just think of these wires as being these simple sort of RC kind of elements anymore. We actually have to treat them as something else. And in particular, the so-called something else is a transmission line, okay? So by the way, just for the sake of, let's say, my own information, how many of you guys have seen transmission lines before? Okay, very good. So I won't spend too much time on this. I'll maybe just kind of draw what my picture of a transmission line looks like to make sure everyone's kind of clear on it. But the typical way you sort of will draw, the symbol for these transmission lines is you kind of have this, hollow cylindrical thing that's kind of indicating it's not really just, a little piece of wire, but it actually has some physical dimension associated with it. And you would typically basically have something that would look like this, where you apply a voltage onto sort of a center conductor relative to a ground, and you pull out that voltage on the other side, and again, of course, relative to the ground. Okay? So, the most important properties of these transmission lines are basically, number one, that it has delay, right? Because remember, the speed of light is finite, so it means that if I do something off on this, in this part of the world, it's going to take some time before anybody some finite distance away can notice that effect happened, right? And that's, again, completely set by the fact that the speed of light is finite, okay? So if I have any sort of physical dimension to this transmission line, it has a delay associated with it, okay? Now, the other sort of implication of that is that, oh, yes, question?
So the delay really with the speed of light is kind of is different than the delay associated with charging and discharging capacitor.
Okay, so the question was, is this delay that's associated with the speed of light different than the delay that's associated with charging and discharging a capacitor? So I'm going to show you a model in 1 second that in some senses will say that they're somewhat equivalent. But having said that, the real big difference between sort of these RC type of line, which is on the chip, versus this so-called transmission line, is that in the RC line, that's basically what's called a diffusive kind of thing. So you really are literally limited by just how fast this resistor can charge a capacitor, okay? Whereas in these transmission lines, then it's really much more about literally just what is the speed of light in that particular medium, okay? So, and I'll draw a model that'll hopefully make that more clear in 1 second as to what I'm saying. So if you didn't quite get it now, maybe give me a few more minutes, okay? Okay, so given that basically if I do something over here, I can't actually notice that it happened until sometime later, that kind of implies that I actually have to store some energy or get some energy to move along that line right? Because otherwise, there's no way for me to actually create that delay in the first place, right? Because if I didn't have some way of storing or moving energy around, then there's no way for me to sort of delay that information from getting to point A to point B, okay? So the simplest way actually to often think about these transmission lines is just say, well, look, if I have some conductor with, let's say a ground plane around it or underneath it or something like that, there's always going to be energy stored, for example, in the magnetic fields due to the current flowing through that conductor, as well as in the electric fields, meaning the capacitance of that conductor to whatever is around it, okay? So one of the sort of, let's say, most intuitive ways of modeling these transmission lines is actually to just think of it as a bunch of small inductors and capacitors. Okay, so let's say that this was my source over here. Right, the energy I stored in the magnetic field is equivalent to just saying there's some inductance associated with that wire. And the energy I store in the electric field is equivalent to saying that there's some capacitance in that wire. Okay? And so again, one of the sort of easiest ways to model this thing is to just break that long wire up into a bunch of these LC sections. Okay? And of course, these are sort of the terminals over here. So now this actually, I think, gets to your question about, well, what's really causing this delay? Well, in this model, you can think of the delay as coming from just, if I put, for example, a voltage over here, it then takes some time to charge this inductor up in terms of the current. That current then flows into this capacitor, right, to increase its voltage. Then the voltage increases the current in this inductor, increases that capacitor, and so on and so forth. Okay? So in other words, in the normal on-chip line, you were basically limited by the resistance charging a capacitor. Here, it's really basically the inductance charging a capacitor, the capacitor then charging an inductor, and so on and so forth. Okay? Does this make sense to everybody? Or? Okay. So the last sort of characteristic that's actually going to be very important for everything else that we're going to be talking about here is a so-called characteristic impedance. Okay, so the idea here is very simple. If you remember, hopefully back in one of those first intro EE classes you took, they showed you these structures where they said, we have some infinitely repeated structure that has, like a resistance, another resistor, and a resistor, and so on and so forth. And they asked you, well, what's the resistance looking into that structure? Well, you can actually apply the identical concept to figure out what the sort of impedance of a transmission line is as well. Okay? So hopefully you guys all remember this is a very famous result, but if this is L and this is C, and what I mean by that is the sort of incremental inductance and incremental capacitance per unit length, then the characteristic impedance of this structure is just square root of L over C. Okay? And it turns out that indeed, this is usually, at least especially in the model that I've drawn here, this is a real number. In other words, the transmission line just looks like an actual resistor. Okay? And by the way, the reason for that is kind of simple. It just says, remember, at the end of the day, all this is trying to model is that it took some time for you to get information from point A to point B. All this impedance really says is that initially, when you try and put energy into that system, or you try and launch some information, what's the sort of resistance that you see due to the line by itself? Because remember, you can't know anything about what that is actually at the load yet. Right? You can only know that after the information has actually traveled to the end of the line and then come back. Okay? Okay, so turns out that basically simply because of the fact that you have this delay and some sort of energy storage, there's some very interesting stuff that happens to these transmission lines. Is there a question? Or?
Yeah, is this result from the wave equation?
You can also derive this from the wave equation. That's correct. I like to think of it in terms of this sort of incremental model, but you can also derive it from the wave equation. Okay? So, particularly in the context of these high-speed links, and let me maybe go back to that earlier picture. Oops. Oh, that's fun. Okay. Fortunately, we didn't have to lose too much in terms of drawing. Okay. So, the reason why I spent some time talking about this transmission line stuff is that, again, if you sort of think about what's happening in any, let's say, realistic system that we might be interested in, you're not necessarily just going to have one sort of simple line from point A directly to point B, right? What's usually going to happen is, you're going to have these bends. It's a little bit hard to see, but you might even have to have transitions from one layer of the PCB to another, right? So you're going to typically get these things where you're not really just going to have one transmission line, but you're actually going to have one transmission line talking, for example, to another transmission line or to a different load inside of the chip itself. And so you have to sort of think about what is that going to do to the sort of signals that we send from one side to the other. Okay? So in particular, what basically happens is that let's just assume from whatever reason that we have one transmission line with an impedance or characteristic impedance of Z1, okay? And we have a second transmission line with a characteristic impedance of Z2, okay? So if you think about it in this kind of structure, when I launch a wave that comes from this side, and let me actually just define that as being VI, right? When I launch some voltage that starts propagating across that transmission line, when it gets to this junction here, there's really only two things that can happen, or really two things that actually happen simultaneously. One is that some percentage of that voltage actually continues down the next transmission line. Okay, so let's just call that V transmitted. Okay? But because it is indeed a wave, and because there might be some impedance mismatch there, and we'll see how this works in 1 second, the other thing that can happen is that I can actually reflect some of the voltage to go back towards the source. Okay? So let me just call that V reflected. Okay? So my guess is a bunch of you have sort of seen the results I'm about to quote in 1 second. These are so-called the telegrapher's equations. But let me just tell you how you'd actually get to them. Okay? So the way you'd get to them is just to realize that if I look at this junction, there are really only two constraints that have to be true. The first is that KVL still holds at that node, meaning the voltages have to be equal to each other, right? So if I use that constraint, that basically says that the input voltage plus the reflected voltage, right, which is kind of what's going to the left or what exists on the left, has to be equal to the transmitted voltage. Okay? Because again, if you think about it, if that constraint is not met, the voltage is unequal on the two sides, and really, then the two of them can't be shorted together as I'm showing. Okay? The second constraint is another sort of hopefully very obvious one, which is that I haven't drawn any lossy elements here, right? There's nothing that can actually dissipate power. So that means that whatever power I put into the system in the first place has to be conserved. Okay? So by the way, you guys tell me, back at the beginning of time, when I applied this VI onto that first transmission line, how much power was I sort of using? How much power came out of my source?
VI squared over Z1.
Yeah, exactly. It's VI squared over Z1. Okay? So if that's the sort of source of power I had in the first place, then now you guys tell me, what does that have to be equal to at this junction? So how much power, for example, am I going to be sending down the transmitted path? Yeah, exactly. That's just going to be V transmitted squared over Z2. Okay, and then how much is coming back on the reflected path? Okay, so now we have to be a little bit careful. So due to that voltage wave that's coming back, the reflected wave, how much power is it actually sending back on the line? There we go. It's V reflected squared over Z1. Okay? Now so the confusion here, which is very common, is it is correct to say that at this node right here, the voltage is VI plus V reflected. But remember, the question we're asking is how much power am I actually sending back? Right? How much power is actually going backwards? Okay? And if you look at that, indeed it's V reflected squared over Z1. Okay? That's not to say that the power sort of at any one node is V reflected squared over Z1. I'm just asking how much power came back. Okay? So, if you take those two together, what it'll tell you, you can then actually go and solve for what the transmitted and reflected voltages are as a function of Z1 and Z2. And what you end up with is basically the following. So the transmitted voltage is 2Z2 over Z1 plus Z2 times the input voltage. And the reflected voltage is Z2 minus Z1 over Z1 plus Z2 times the input voltage. Okay? Now, if you look at these pretty carefully, it actually tells you something pretty interesting, right? So just as an example, let's say that I made Z2 an open circuit. Okay? So how big would the transmitted voltage be relative to the input voltage? Yeah, it would actually be twice as large, right? So now, is something wrong? Like, did I break some physics here, or is this actually totally okay? Like, how in the world did I get the voltage to actually magically double? Ah, okay, so you said everything is being reflected back, but, let me just draw sort of exactly the model of this situation. Okay? So let's say this is my input voltage here. Let's say it has some source resistance, okay? And then it's driving that transmission line, and what we're basically saying is that on the other side, we just have an open circuit, okay? Just to make, let's say, life more clear, let me assume that that source resistance is 50 ohms, and that the transmission line itself is also a 50 ohm characteristic impedance, okay? So, right at the beginning when I launch that input, what is the actual voltage going into the transmission line? Yeah, it's half VI, right? It's VI over 2. Okay, now, at the end of the day, after you wait for this transmission line to do whatever it's supposed to do, what should the actual final voltage on the end of the thing end up being? Yeah, it has to be VI, right? So notice there's exactly this factor of 2 difference between what the final voltage was supposed to be and what you initially launched onto the line. Okay? So all this is saying is that indeed if you have some open circuit like this, it's not to say that, because that there's something happening that was wrong with that doubling. It was just saying that this is the mechanism by which the transmission line is basically enforcing that indeed what is really placed on the input should eventually show up on the output. Okay? And so it turns out that both in terms of the transmission and in terms of the reflection, you get some things that look really weird. For example, the reflection, you can even get like negative waves going back. It's really just saying that it's just trying to balance things out on the two sides so that if you waited forever, indeed, you'd actually have what you were supposed to get just from thinking about it as a completely DC circuit, right? That if you just had a wire from here to there, indeed, you should just end up with the input voltage at the output, okay? Now, why did I spend all this time talking about this? Well, in our particular context, what's really important about this is that if you're not very careful with basically what you do either first at these junctions, or second, even what you do at the transmitter and the receiver, you can actually introduce some really nasty, basically, distortions or errors in your communication path. Yes?
Sorry, just to clarify this. So in this case, when you're saying that the Z2 is basically an open, I guess I'm not totally sure on this example here why the transmitted voltage is twice the reflected voltage.
Oh, because notice the actual input into the transmission line is VI over 2.
Oh, okay.
Right? It's not VI, it's VI over 2. Because at the beginning of time, you really have to model that transmission line as being a 50 ohm resistor to ground. Right? Once that wave gets over to here, it says, oh, oops, there isn't actually a 50 ohm resistor to ground. It's actually an open circuit. So the voltage that's supposed to show up at the end should actually be VI, not VI over 2. And there will also be a reflective wave coming back, which will actually come back, and once it gets there, it'll say, hey, by the way, you were actually supposed to be double what you thought you were.
But wouldn't that mean that it seems like the transmitted wave should be VI over 2 and then reflected should also be VI over 2?
That's correct, but when we say the transmitted wave, because this is stopped here, it'll say that the voltage that actually shows up here is just going to be VI. Right, so in other words, the transmitted wave will indeed be VI. Or, excuse me, let's be careful. So let me just, to be totally clear, like what I really mean is that if we look at this picture right here, this equation is relative to the voltage that shows up at the input of the transmission line, not at the voltage source over here. Okay, so again, what I'm basically saying is that if you originally sent in VI over 2 into the transmission line itself, at the end over here, the transmitted wave would indeed just be the original VI at the very input. Okay, great. All right, so again, the only reason we spent some time talking about this here in this context is that it tells you it's actually very important to be very careful both with how you construct that physical connection between the two of them, and that even if you have a very clean sort of connection, you better be sure that at both your transmitter and your receiver, you actually terminate it with the correct impedance, meaning you really want to use whatever the impedance of the transmission line is to actually grab the energy coming out of it. Because if you don't, what will happen is you'll get these forward and reflected waves. And then as an example, if you sent, let's say, a 1-0 pattern over here, well, it would go through this thing, reflect off, and come back. And if there's any other weirdnesses happening inside, you might actually not really get this pattern at the receiver. Instead, you might get some other weird-looking thing. Okay, where that weird-looking thing is just related to all the additional reflections you did inside of that communication channel itself. Okay? So, I've been talking about these transmission lines so far just really in terms of their delay and what they do with, causing reflections. But, of course, they're never really ideal. They always have some loss intrinsically in and of themselves. And there's really sort of two important mechanisms. One is the so-called skin loss, which is just related to the fact that at high frequencies, the current only likes to flow on the edges of the conductor in order to minimize the overall impedance. That means the resistance goes up, and so therefore you actually get additional loss due to that. Secondly, there's also the so-called dielectric loss, which is just related to if you have an AC electromagnetic field, or particularly, let's say, just an electric field, there's always molecules in the sort of, let's say, dielectrics around it. And when you apply those fields on them, the molecules can't basically follow those fields infinitely quickly. So what ends up happening is you actually get some sort of drag on those molecules, which ends up being, again, another form of loss. Okay? So particularly at very high frequencies, these losses can actually be quite nasty, because as I indicated in the slide, they're proportional. Let's say the skin loss is square root of frequency, and the dielectric loss is proportional to frequency, but they're both in dB. Okay? So that means that if you double the frequency, you double the number of dB of loss that you got. Okay? So that very, very quickly actually adds up. All right? So this is going to be, let's say, one of the main mechanisms by which what you transmitted over originally will not actually show up and look the same as it did on the receiver. Okay? The other issue is that, as I was mentioning before, it's very easy for you to actually get things that are not just these straight continuous transmission lines, but instead have all kinds of nasty, let's say, discontinuities along the way. One very common one is this so-called via, right? So, as an example, if you want a via from the upper layer to, let's say, one layer below it, unless you have a somewhat more complicated PCB manufacturing process, the way you typically do that is you have to build sort of a piece of metal that goes all the way through the entire PCB, right? Well, if you think about it from our sort of transmission line standpoint, the equivalent model we're going to have is something that looks like this, right? We're going to have a transmission line. Then you can see this piece right here is very, very short. So we're going to have essentially another transmission line kind of representing all of this stuff down right here. And at the end, it's just open circuited, right? Or at most, it maybe just has some capacitance sitting there, right? And then, of course, we have the rest of the path that kind of goes like this. So I'll actually maybe just draw it only up to this point right here. Now we have another transmission line like this, okay? Well, what's really nasty about this particular structure is that, as we said before, right, if I send in some data or some edge right here, when it gets to this point, some of it will go forward, some of it will actually be reflected back, but some of it will actually go down this transmission line right here, right? And what's particularly nasty is that when it goes down right here, when it sees that open circuit, it's again actually going to come back and reflect back to this point right here. Well, let's just say that you happen to get unlucky. Oh, yes?
Sorry, if your circuit is in like the first level, why do you have to make all those vias if you don't have a circuit?
So this is what's called a through-hole via. And this just has to do with the PCB manufacturing process, where if you didn't want to end up with something like this, what you have to do is one of the following two things. Either you have to take this sort of metal slug that you poured into there and back drill it, and then you have to sort of, let's say, pray that you drill it to exactly the right depth. Or you have to do what's called a blind via, which is you have to sort of do this and then fill this all in with FR4, which again, it's not that it's impossible, but it's more expensive. Okay, so in a standard manufacturing process, this is exactly the kind of via that you would get. Good question. Okay, so again, the really big issue with something like this is that what can very easily happen is by the time this thing has gone down this transmission line and come all the way back, you could just so happen to be very unlucky, and the phase of that has actually completely flipped over. Okay, so just imagine that for as an example, over at the transmitter, I was sending like a 1 0 1 0 1 0 pattern, right? Well, if I just so happen to get unlucky and the delay across this transmission line going across it twice happens to be a 180-degree phase shift at that particular frequency, well, guess what? The wave that's going to come back is exactly going to cancel what you sent into it in the first place. Okay? So, turns out that kind of effect usually results in these pictures that I'm showing you here, where you have these so-called notches in the frequency response. As you can imagine, if really at some particular frequency you just basically completely eliminate your signal, very, very bad in terms of trying to receive it on the other end. Okay? So what I'm showing you here is some example so-called channels. And what I'm showing is actually sort of, you can think of it as just the transfer function of, if I send something at the transmitter, what shows up at the receiver? And I'm showing it here in the frequency domain. Okay? So what you can see is that, let's say I look at about 3 gigahertz here or so. I typically have anywhere from about 20 to 30 dB of loss. Okay? And of course, depending upon exactly which channel I'm looking at, I can get pretty wide variations in those characteristics. The question we really have to ask ourselves is, how bad is that? In other words, if I really have this 20 or 30 dB of loss, what does it say about my capability to actually run a link and not just get it to run at a certain speed, but actually do it within a reasonably low amount of power consumption? Okay? So to answer this question, which we'll start on today and finish on next time, there's really sort of 2 related issues we have to think about. Okay? The first is really related to sort of something that we've been talking about quite a bit throughout the course of the entire semester. And that's really just, okay, if I have this much loss, that implies my signals are going to be smaller, right? If my signals are smaller, I better make sure that they're big enough compared to my noise to make sure that I actually get the data I wanted back in the first place. Okay? The second issue, which again we'll cover more a little bit later on, is the so-called intersymbol interference. Okay? The idea here is very simple, which is just to say, if at the transmitter I, for example, sent some pulse of data like this, well, if I have this low-pass channel like what I'm showing you here, what I'll get at the receiver will look something kind of like that. Okay? And in particular, if this thing really only spanned 1 bit in time, now if I have something like this, actually even for times well after that first bit, I'm still going to have energy hanging out from that originally transmitted thing. What that basically means is that those bits are going to be interfering with each other, right? Because if I then try and send another bit at some time later, instead of getting a nice clean 1 or 0, instead I'll actually have something that's, basically still got some energy from the previously sent bits that will mess up my analog voltage. Okay? Again, we'll talk a lot more about this next time. I just want to make sure that I cover sort of one important concept here so that you guys can really actually get going on the project. Okay. So the most important thing that I want to make sure we finish for today is, again, really this issue of that first issue of just, how much noise can you actually tolerate? Okay? And so the reminder here is really just to say that obviously any receiver circuit you build is clearly going to have some noise in it. Okay? Now, by the way, the simplest receiver you can think about is basically just some kind of a comparator. Okay? Because after all, if I'm just sending digital 1s and 0s at the transmitter, and then they come across the wire, if the wire, or the transmission line I should say, is kind of a nice clean transmission line, then at the end, really all I have to do is decide, did the transmitter send a 1 or did it send a 0? Right? So the easiest way to do that would just be to have some comparator whose threshold was sitting right around, let's say, the differential 0 volts. Right? So to be totally clear, if my transmitter is basically sending, let's say every time it sends a 1, it sends a voltage of plus delta V. And every time it sends a 0, it sends a voltage of minus delta V. Right? So if I want to know if some particular transmitted waveform is a 1 or a 0, then at the receiver, again, really all I have to do is just look at, relative to 0 volts, did I send something that was above it or below it? Okay? So again, that just implies that indeed my receiver is typically just a very simple, at least not typically, but in the simplest case, is just a simple comparator. Okay? So, the trick here is, of course, that this is all in the ideal world where I have no noise. Right? But because I do actually have some noise in this comparator here, what can potentially happen is that once I add noise into that thing, if the noise is ever larger than the signal I transmitted, right? So that if, for example, let's say I transmitted a plus delta V, but the noise pushed it all the way down below that switching threshold, well, instead of receiving a 1, now I'll say that I actually received a 0, right? Because again, the only way I decide what's a 1 and what's a 0 is just by looking at what's above or below that threshold. Okay? So in particular, the way that we sort of capture that is with this so-called bit error rate. Okay? It basically tells you, on average, per unit time, how many bits out of the total number of bits that you sent did you actually get incorrectly. Okay? And by the way, just to give you some sort of typical numbers, for the kind of systems we're talking about, you typically need something on the order of anywhere from 1 to the minus 12 to 1 to the minus 20. Okay? In other words, for every 1e12 bits you sent, only one of them should be wrong, right? Or even more aggressively, for every 1 to the 20 bits you sent, only one of them should actually be wrong. Okay? Turns out these kind of specs are typical just because, at the end of the day, if you're playing, a video or you're sending an email or something like that, you get really unhappy when, you typed, "Hi, my name is," a lot, and instead it comes out, "Hi, my name is Bob," right? Because you just don't want that darn bit to be wrong. Okay? Okay. So, the way we're actually really going to use this from a design standpoint is to basically say, if we're doing the design of this link, then basically we really just need to know a couple of things to figure out what's actually our bit error rate going to be. Okay? So before I sort of explain that, let me just briefly explain kind of what these funny looking pictures right here are, because they'll be useful to actually answer this particular question. So the picture I'm drawing here is what's called an eye diagram. Okay? And the idea is very simple. So imagine that I was to look at the stream of bits, or the stream of, let's say, voltages that I sent at my transmitter and then showed up at the receiver. Okay? So if everything was ideal, then if I send all these sort of nice, clean digital bits at the transmitter, they would come back and also look exactly like these square wave waveforms at the receiver as well. Okay? So what this eye diagram is doing is basically saying, well, over the sort of, in this case, a period of 2 of those transmitted bits, instead of sort of showing this all linearly in time like this, let me take each of those waveforms and overlay them back on top of each other, all to sort of sit onto the same period of that 1 2-bit stream. Okay? The reason this is useful is that if you think about it, if I really had a perfect communication system, then when I draw that picture, what I should basically see is these kind of boxes like this, right? Where these vertical edges basically just represent when was there a transition in the data bit, and the horizontal lines here just indicate how big was the voltage that I was receiving at the receiver that indicated either a +1, or meaning a 1, or a 0. Okay? Now, of course, you never really get something like this, because in reality, even the transmitter never has perfectly sharp edges, right? There's always some variations in the actual voltage levels. So instead, what you typically get is, these things with kind of rounded corners like this, right, which is just representing the sort of transition time. And you'll see that there might even be some sort of fuzz in the upper and lower levels there. Okay? So now hopefully you can see why this is typically called an eye diagram, because once you make them look sort of realistic, these shapes sort of look kind of like an eye. Okay? Like they're sort of squinted or whatever. Okay? So the whole trick here is that when I look at this eye diagram, if I want to know sort of how often I'm making an error, it's really pretty straightforward. Okay? Because it really just comes down to, if I take this comparator that I'm using as my receiver, remember, at the end of the day, all I care about is, at a given sampling time, is the voltage I received above or below the threshold of that comparator? Okay? So let's just pretend, for example, that I set the threshold of my comparator to be right there. Okay? And by the way, I think you guys have this picture, at least in some form, on your slides already. Okay, so by the way, you can notice here I intentionally drew that threshold as not being at the ideal point, right? Because in reality, any comparator you build will always have some residual offset in it. Okay, so as an example, let's say you really wanted that threshold to be exactly at 0, which would be the center line right here. Well, due to non-idealities in the circuit, which again we'll talk a lot more about later on down the road, you could very easily have some shift in that threshold there. Okay? So now the whole name of the game in terms of figuring out your bit error rate is just figuring out, well, given that this is actually my threshold, if this is then the sort of signal that I received, and this is just, let's say, just the ideal signal coming from the transmitter, then now what I need to see is, if I was to add some noise from the receiver, and let me do that in a slightly different color. So let's just call that, some voltage noise here. Well, that voltage noise is going to have some, let's say, Gaussian distribution around that threshold, right? So the question really becomes, how often is that voltage noise going to be large enough that actually it's going to take a sample that would have been above my threshold and actually make it look as if it's actually lower than my threshold, right? Because if it is, I'll then actually make a mistake, right? I'll actually interpret it as being a 0 instead of a 1, or vice versa, of course. Okay? So the whole name of the game here in terms of calculating, what that bit error rate actually would be, is basically just to look at that essentially distribution of the noise and figure out how much area is there basically in that region that's essentially sitting at the edge of my received signal, right? In other words, anytime the voltage noise is larger than the lowest signal I received from my transmitter, then I'm actually going to make a mistake, okay? So the way you actually calculate this, for those of you guys who haven't seen statistics in a while, is through the so-called complementary error function, okay? So all this equation is really saying is that if I want to know what my bit error rate is, I first have to look at just how big is my transmit voltage. In other words, how far from that threshold is the lowest thing I can actually get. Okay? That's what this V in minus V off is indicating, right? V off is just, where is the threshold of the comparator? And V in is just how big was the transmitted voltage relative to 0. Okay? This kind of tells me the net distance I have to work with. And then what I do is I basically compare that to the standard deviation of my thermal noise. And by the way, this is assuming everything is Gaussian in terms of the noise here. Okay? So if you take this complementary error function, that's really just telling you how often is it that the noise is larger than this distance right here. Okay? So by the way, this complementary error function is a real pain in the butt to compute, so I actually never do it. Instead, what I always do is just remember these numbers that I've indicated down below. Okay? So basically, if, for example, you want a bit error rate of 10 to the minus 12, it basically tells you that what's up here in the numerator, meaning the amplitude minus the offset, has to be equal to 7 times the thermal noise. Okay? Similarly, if you want a bit error rate of 10 to the minus 20, then basically the distance that you have available to work with has to be 9.25 times the standard deviation of the thermal noise. Okay? And there's just a few of these numbers that are sort of fairly common. So for example, if you want 10 to the minus 15, I believe that's about 8 sigma. But basically, I just remember it in terms of this. You can think of it, by the way, very much like a signal-to-noise ratio. Right? In other words, how many sigma of thermal noise do you have to be able to fit into your signal to guarantee a certain bit error rate? Okay? So I obviously rushed through this. Any questions before we sort of break for today? Or I just wanted to make sure we cover this because this is kind of the first critical thing you need to know in order to be able to start phase 1 of the project. All right, so if there's no questions, obviously, in class at least, I'll be available. Oh, yes?
So for these two bit error rate numbers, why isn't there the sigma noise in the equation?
You mean, because what I'm basically saying is I'm just trying to sort of reverse it in the sense of I'm just saying, look, rather than me sort of calculate this overall equation each time, I'm instead going to go in the other direction and say, if I want to get a bit error rate of 10 to the minus 20, how big does my effective signal have to be relative to the thermal noise? So in other words, just interpret this as that signal over the sigma has to be 9.25.
So the sigma n is really sigma noise.
Exactly. I'm sorry. Yes, the sigma n is really the sigma noise. Yes. Okay, great. So we'll see you guys all on Tuesday.